Today I want us to look at the application of derivatives. The application of derivatives are not, it's not like there is much of a strategy or principles that are there. I want to show you how the derivatives are actually used in real life, if there are certain things that you wanted to calculate in real life. And another thing, some people who usually have an understanding of how the mileage work and other things that can be checked within the car. If let's say there is an accident, you will find out that there is a built-in application of derivatives in that process. So I want to give you some of the examples so that you get familiar on the application of derivatives, and I think I will give you just about 5 examples of how to apply derivatives in real world. The first example is saying the position function of a particle is given by this function here, which says s of t is equal to 2t cubed minus 5t squared plus 3t plus a 4, where st is measured in centimeters and t is in seconds. So this function here is a position function. In other words, it determines where is the particle at some time t in seconds. And another thing that I want you to realize here, I want you to still remember what is the velocity in terms. If you are given a position function, what is the velocity, what is an acceleration, and actually what is a jerk. Usually the jerk is not really, we don't usually examine it much. I mean, the reason behind is that the concept of a jerk is not really something that is mostly used. So we usually want you to know how to find the position of the particle after 2 seconds, find the velocity, and find the acceleration. And we usually end there. We don't usually talk much about the jerk. So this question, the first question is saying find the position of the particle after 2 seconds. And if you notice here, this is the position function. In other words, if I am plugging in here 2 seconds, I will find the position of the particle after 2 seconds. So these are the solutions to these questions. So A is saying that you are actually looking for S of 2. So where there is t, I'm just gonna plug in 2 seconds, and then of course the function was supposed to be 2, and then here I'm gonna end up plugging in my 2, and then I cube it, and then minus 5, and then I plug in a 2 there, and then I square it, and then I plus, and then I have a 3, I plug in a 2, and then I add a 4. You can work these things one by one by hand, or use a calculator just to make this a little bit quicker. You know that 2 cubed is 8, and then you know that 2 squared is 4, and then you can work this thing by hand. But to save time, instead of having a long video, I'm just gonna use this calculator here. So I'll have a 2, and then I'm gonna have a 2, and then I'm gonna end up using a 3 there, and then I'm going to subtract 5 times 2, and then I square it up, and then I'm gonna add 3, and then I'm gonna plug in a 2 there, and then I'm gonna add a 4, and then the final answer should be 6. And now the units were actually given to us that it is centimeters, so this is supposed to be 6 centimeters. So the particle will have moved by 6 centimeters after 2 seconds. And then find the velocity of the particle after 2 seconds. We know that the velocity is in meters per second. In other words, it is the first derivative with respect to time of this position function here. So we know that we have s of t, and s of t is 2t cubed minus 5t squared plus 3t plus a 4. So we are having that function there. So if we are looking for the velocity with respect to time of this particle, we are actually looking for the first derivative of this function, or s prime of t. And of course, if I wanted to take the derivative of this, I just need to take a derivative of that, derivative of that, take the derivative of that, and then I can sum them up just to find the difference there. So let us look into this. So the derivative of this, of course, is going to be 2 times and then 3. I'm going to bring this 3 down. Remember that when you're taking a derivative, the constant, you always pull it out and then you take the derivative of this part here. So the derivative of this part is going to be 3t, and then I subtract a 1 there, so I'll end up having a 2. So there is a multiplication there, and then minus 5. I'm pulling this one out, and then I'm taking the derivative of this. So when I'm taking the derivative of this, I'm going to have 2t, and then I will subtract a 1 there, and then I will just have a t, or just 1. And then plus, I'm gonna pull out the 3 and then take the derivative of t, and the derivative of t is going to be just a 1, or the slope of this function here is just going to be this gradient, or this constant here, which is 3. So we have that, and then the derivative of this, of course, the derivative of a constant, because a constant function is not changing, so it's just gonna be a 0 there. So I'm going to add a 0. Of course, if I proceed here, you will find out that I will end up having 2 times 3, which is 6t squared, minus 5 times 2, we know that is going to be 10t, and then for this one here, I know that is just gonna be a plus 3. Just to double check that this times that is a 6, and then t squared, and then this one times that is a 10 and a minus 10t, and then this one is just a plus 3. But the question did not say differentiate this function. It said find the velocity of the particle after 2 seconds. So the velocity of this particle after 2 seconds is going to be v of 2. So where there is a t, I'm gonna plug in 2 seconds. In other words, it is going to be the same as s prime of 2, which is the same as, I'm going to have a 6, and then in the value of t, I'm going to plug in a 2, I square it up, I minus a 10, and then I'm going to plug in a 2 again, and then I plus a 3. So the answer that I'm looking for here is actually going to be, let me put this, so I'm going to have a 6, and then I have a 2, and then I square it up, and then I'm going to say minus, and then I'm going to have a 10, and then I'm going to multiply it by a 2, and then I'm going to add in a 3 there, and then of course this is going to be 7. Of course, you know that velocity is a change in position divided by a change in time. So the units for this, of course, it was centimeters, and then this one, the units for it was seconds. So basically, when it comes to the velocity, this velocity is going to be 7 centimeters per second. So that's what is actually happening here, because this one was in seconds, and then this one was actually in this one was seconds, and this one was in centimeters, the velocity of the particle. Now, if you look into the third one, the third question was just saying that find the acceleration. We know that the acceleration is the same as the first derivative with respect to time of the velocity, and of course the velocity is actually the second derivative of the position function. And if we are taking the first derivative of this function here, you'll find out that I have to bring this 2 down, and then when I'm bringing this 2 down, it will multiply that 6, and then we'll end up having a 12t, and then I subtract a 1, and then this one is just going to be a minus 10, because I'm going to pull this out, And if you look into a function that is y is equal to 10x, and you can see that this is the gradient, so of course the derivative, of course the derivative is a gradient of this, or the slope of this. So the slope of this part here, of this function here, we know that is 10. It's the same thing here, that we're actually just having a 10, and then a constant function is not changing at all, so this one is just gonna be a 0. And now if we're looking for the acceleration at t is equal to 2, we know that what is going to happen here, I just need to plug in a 2 here in the value of t. So I'm going to plug in a 2 minus a 10, and of course you know that we have a 2 here times 12 is just a 24, and then minus a 10 is supposed to be a 14. So we have a 12 times a 2, and then minus a 10, we have a nice 14. Because this is actually in centimeters, I'm just gonna say centimeters per second square. So that is actually what is actually happening in this particular question. So I hope you understood that what we're actually doing here, we're just taking the first derivative, the second derivative, and the third derivative when we're actually looking for acceleration and also the velocity. And also, if you look into the velocity here, you will find out that in most cases, most people are usually struggling when it comes to this position. And when we are talking about position, you will find out that in most cases, people don't want to think in terms of a negative position. No, I'm just 5 meters away or 10 meters away. But if you notice here, if let's say I am standing here, I can either go this side or go that side. So if let's say I am actually moving to this side, someone might decide that this side will be negative 5 meters and then this side will be positive, depending on what you are saying that it is actually I am moving up or moving down. And then secondly, if let's say I was moving, let's say this side, I consider moving this side a positive side and moving this side a negative side. So if the car is actually moving this particular direction, so as long as it is moving this way, I can think of, okay, as I'm moving this way, this one is actually increasing if I'm moving this side. And then if I'm moving this side, I'm actually moving in a very negative direction, or in the negative side, right? And then when we're talking in terms of velocity, if I am moving this side, then I can also say that my velocity is going to be positive. And if I am moving this side, I can also think of my velocity is actually negative, so it is decreasing. So that's what is happening with position, so it is decreasing. And when it comes now to the acceleration, you see, like when you're pressing your accelerator in your car, you will find out that sometimes you're speeding up, sometimes you are speeding down, sometimes you are just moving at a constant speed. For instance, let's say you are moving at 100 kilometers per hour, and in a very ideal situation, there are no cars in the road, you can have that speed. But in most cases, you'll find out the speed is going down, up, down, up and down. You are seeing a dog in the road, so you have to slow down. Or you are seeing a human being who is drunk and they don't want to stop and wait for the car to pass, they're just moving to the road, so you have to slow down. So in those cases, you will find out that sometimes you're speeding up or you're speeding down, but you're still moving in the same direction. So when it comes to the acceleration is characterizing if is this function at that moment in time speeding up or is it speeding down. That is the meaning of this particular acceleration. So I want us to take another example now, which has nothing to do with acceleration, position, and velocity. Let me write it down first, and then we can look into it. So the second example is saying, suppose Ms. Mvelo's company can produce a maximum of 1,500 widgets in a year. Then their profit in rands is given by this function here, which is saying P of X is equal to 30 million plus 750x squared minus 1 over 3x cubed. How many widgets should they try to sell in order to maximize their profit? So let me also specify something here which is much more important, is that how do we end up getting these functions? So you will find out that in most cases, if let's say someone is asking you, can you model this business? Is it gonna make profit? Is it gonna make a loss? How much are the costs? How much are the costs? And also how much is the profit that we can make? Or operational income, or all those things. So what usually happens, you will find out that someone has a recording here, and this side they have time, and this side here there is money in rents. So they record here, let's say maybe we have day 1 from the business, 1, 2, 3, 4. Time can either be days. So after 1 day, how much have you made? If let's say you are selling, how much have you made in profit? Maybe this one is 10 rand, and then after the second day, how much have you made in profit, including the profit that you made there? Let's say maybe here you have 20, and then here maybe you have 35, here and here you have 40. So if they are recording, you can have a column here that is saying that, okay, this one can say that on day 1 I made this profit, day 2 I made this profit, day 3 I made this profit, day 4 I made this profit. Or someone might decide that in day 1 this is the profit that I made, and then in day 2 I'm going to combine that profit plus the new profit that I made here. So it depends on what is happening. So what is important here is that you have a time, and then you have money this side. So what you do, you either use one of the softwares I told you earlier, and then you go to the Excel file, and then you add the spreadsheet there. You add this time in the first column, and then you add these numbers in the second column. And then once you do, you use you approximate the function, and then the function you get might be something of this kind. That's how we usually get these functions. But for now, we're not getting the functions. We wanted to analyze them and solve questions. So this question is saying, how many widgets should they try to sell in order to maximize their profit? When you are selling, I mean, you want to make sure that you're making profit, because if you're not making profit, you're making a loss, and if you're making a loss, it's going to eat in your pocket. So what is important here, I want you to understand that the value of X, so this is the solution. I want you to understand the value of X, right? So if here you have to sell, you cannot say that I've sold negative things. That cannot happen at all. So you can either sell 0 widgets, so we cannot say we sell the negative things. So here you will find out that X is always gonna be 0, or a number that is above 0. That's what I want you to realize here, that X is 0, or a number that is above 0, because you cannot say I sold negative 5 widgets. No, it's either you sell or you don't sell. When you are selling, you will have positive things, but here they are saying that the company can produce 1,500 widgets. So if they want to sell, they cannot sell more than 1,500 widgets, because this is the maximum they have. So the value of X, which is the value of X, so we cannot sell more than 1,500 500. So x is a value that is between 0 and 1500. I hope you can catch that, because this is very important, because this thing is just saying that our x is always going to be above or equal to 0, or it's always going to be less than or equal to 1500. Now, how many widgets should they try to sell in order to maximize their profit? What is important about this function is that this function is a polynomial and it is continuous everywhere. So if you want to find the maximum value here, suppose you were going to draw this function. I'm just going to make a guess. It's not educational. I just want you to actually understand what I'm saying here. So suppose you knew how to draw this function and you found out that this function here is just suppose you have this function and you find out that this function is a function of this type. So it's a function maybe that is going like this, right? So it is of this type. So if you want to find the maximum value, so the maximum value that you can get, right? I want to explain two things at once. The maximum value that you can get, or the minimum value that you can get of this particular function, can either happen at this point here, which is the minimum, or can either happen at this point here. In other words, it can either happen at the turning points, or if let's say 0, suppose that I have 0, 0 somewhere here. So this function, of course, is going to continue and all the way. So because my x here is starting at 0 and end at 1500, this one here where x is equal to 0, I'm going to cut my function and say it ends there, because my x or my domain started at 0 and end at 1500, and this one, my x is 1500 here. So I am going to cut my function here. So basically, so if I am looking for a maximum value, I have to check at that value here, which is the beginning or the end point of this interval here, or the end point of this domain. And also I have to check this point here, and I have to check the end points, and then the value that is highest is going to be the maximum value, and the value that is lowest is going to be the minimum value. That is why when we are solving min and max problems, we don't only check the turning points, we also check the endpoints, because it might happen that we are having a maximum value at the turning point, or it might happen that we are actually, this point here is way above the turning point. That is why we have to check this one and that one for the turning point. I mean for the maximum value, and also for the mean we have to check this one and that one. And in most cases you don't know how this function look like, you can't draw it. So what is important for us is that you just need to check this value, what is the output of this value, check the output of this value, and then you check the outputs at the turning points, and then those outputs will actually tell you which one is largest in all of them. That is why I was trying to explain this thing. I hope you can get what I'm trying to do here, that you are actually checking the turning points and you are also checking the end points, because you know that if a function is continuous, there are no gaps in between, and the only point where we are going to get the maximum value or the absolute maximum is when you are checking all these points, either at the turning points or at the end points. So what we are going to do here, we're gonna start with this. So we're gonna say that when x is equal to 0, then p of 0 is equal to 30 million. So you have that 30 million, and then 30 million, and then you have plus, and then you have 7, 5, and then here we're gonna plug in a 0, and then minus 1/3, and then you have a 0, and then you have that cube there. So basically this is going to be 0 and this is going to be 0, so you will end up having 30 million rands, right? So if I am not selling anything, then the profit that I'm going to make is this much. So if we are selling nothing, and then now if let's say I sell everything, in other words I sell 1,500, then what is going to be the profit? So I'm just going to plug in 1,500 in this function here, so I will end up getting 30 million. This is 30 million, and then plus 750, and then inside, of course, I'm going to place 1,500, and then you're going to actually square it up, minus 1/3, and then after that you're going to end up placing 1,500, and then you can cube it. Of course, if you look into this one here, you will find out that for this you just need to plug it inside a calculator here. This is, how many zeros are here? Supposed to be 7 because it's 30. So I have 1 2 3 4 5 6 7. Hope this is right. 1 2 3 4 5 6 7, and then after that you plus 750, and then after that we will end up saying 1,500, and then after that you can square it up, and then you subtract 1, and then you divide it by 3, and then after that you're gonna place in 1,500, and then you can give it a cube there. So the answer that you are getting here is in rands. Of course, you have how many zeros are here? 1 2 3 4 5 6. Okay, so we'll end up having 592, and then we will end up having 500, and then we're gonna end up 1 2 3. Okay, let me make sure that this is this 1 2 3 1 2 3, and then 1 2 3, and you can see here that we have 592 million and 500,000 rands. That is actually going to be a profit if we are actually selling every widget that we are actually having there. Now we have checked the endpoints, but now we need to check the turning points, because we don't know this function, how does it look like. So this is always going to be the process when you're dealing with these minimization problems. And then now we check the turning points. So that's what we are going to do now. Check turning points. So what you do to check the turning points, of course, is very easy here, because what you do, you have your function. I'm gonna use this orange here. I have my function p of x, which was equal to 30 million. We have 6 zeros, and then we had a plus here, and then we had 750, and then we had x squared, and then we had minus 1/3, and then we had x cubed. I know what is usually happening to some folks. Some folks actually think that in order to maximize profit, I need to sell everything. Why do I have to calculate this whole thing? Sometimes selling actually have some costs too. So it's not always the case to just assume that selling everything is actually going to help us. Sometimes you will find out that selling this much is the right way of selling. So once you achieve this much, it's fine, because after that you start to incur some costs. So that is what is important here. It's not always just sell everything. So that is what we are trying to figure it out here. How much should we sell to maximize our profit? And then now, to find the turning points, all you need to do first, you just need to find the first derivative with respect to this inside variable, and then this one here is going to be dx, which is this x inside, and then we have 30 million here. And then after this 30 million, you have 750 x squared minus 1 over 3 x cubed. I know that when you are seeing this minus, some people are usually lying and saying, no, when you are having a minus, it might happen that you are also making some loss while this thing is happening. So this minus here is coming from that loss, or blah, blah, blah. This minus comes from when you are trying to model this thing. You find out that the right equation, because you take this thing as it is and then you find it model and then it gives you this. It's not like it's saying to you that this, no, it's just the model of the numbers that you actually got when you're helping someone to actually model that thing mathematically. So when you're having this, you want to find the derivative of this whole thing. You find the derivative of that piece by piece. The derivative of a constant, we know that is always going to be a constant, and then plus, and then the derivative of this, you multiply this by 2, you bring this 2 down, so you will end up having 750 times, and then the derivative of x squared is always gonna be 2x, and then minus 1 over 3, and then this one, because the constant, you always pull it before derivative, and then you take the derivative of this, and the derivative of this, of course, you know that is going to be 3x squared. So that is actually what is important here, that you bring the x down and then the exponent down, and then you subtract a 1, and then you're left with a 2. And then of course when you're multiplying this, you have 750, and then you multiply it by 2. Of course you will end up having 1500. This one's going to 1500x minus this 3, and that 3 will cancel out, and then we'll end up having minus x squared. And then of course we just need, this is p prime of x, and to find the x coordinate of the turning point, you set p of x to be equal to 0. In other words, we want 0 to be equal to 1500x, or 1500 times x minus x squared. And then after that, you know that all you need to do, because you have an x and you have an x, you can factor x out and you'll be left with 1500 minus x. Of course, now if you are having this here, if you have an output that is 0, it's either this x is equal to 0, or this whole thing here is equal to 0, or both these two are equal to 0. That is why we are saying x is equal to 0, or 1500 is equal to an x, or you can say that 1500 minus x is equal to 0, which means now we are actually landing in x is equal to 0, or x, taking this to the other side, so we'll end up having 1500 is equal to x. So I have x is equal to 0, and I have x is equal to that. And now when we're having these two things, you find out that these are the x coordinate. And then now to actually check if selling this much or that much is actually going to be helpful, you need to find out p of 0. And of course we found that p of 0 was 30 million rands, and which means, and we also ended up having p of 1500, it was equal to 9, let me check here, because that one was actually straightforward. So it was 592, and then we had 500,000. So if you look into this one here, since you can say that another thing that is happening now is because for this particular case, it happened that the end points are actually this the turning points of this particular function. So because that is the case, it's not always gonna be the case, it's just this one is only for this case that it happened that the turning points are also at the same time at the end points. So that is why we are lucky here. But if this x was different from the end points, then we're going to plug and get a different value. So because we are having these things here, what do we actually do? we just say that since P of 0, you can see that 30 million is less than 592 million and 500,000. This one is bigger than that, so we can say that because this one is less than P of 1,500, we say that then selling X equal to 150 widgets will actually maximize the profit. Just a quick summary here is that you first need to make sure that you find the endpoints, and then after finding the endpoints, what you actually do, you want to make sure that these endpoints, you find the outputs by plugging them in the function, and then after that you find the turning points by finding the first derivative, and then you set it equal to 0, and then after getting those, you plug them back to the original function to get the outputs, and then you compare the outputs. After comparing the outputs, you check the final output that is bigger than all of them, and then once you have that final output, you check the X that is associated with that output. That is what we are looking for here. Let's look at this example number 3 here. Suppose the management of Nxana's properties is going to build a new apartment complex. So we have Mr. Nxana, who is so much interested in properties, and he actually found a management for that company, and now they are in a process of building an apartment complex. They know that if the complex contains X properties, the maintenance costs for the building, landscaping, and other things will be given by this particular function here, which means Mr. Nxana have been recording some information, and he realized that after taking this information, he knows that each property usually cost this much, each property usually cost this much, and he actually built a table that have number of properties, and then on the second column the costs. So after using that, he actually found out that the cost equation will be given by this function here. The land they have purchased can hold a complex of at most 500 apartments. So if they buy, if the land they have bought, if they build apartments inside, they cannot build more than 500 apartments. How many apartments should the complex have in order to minimize the maintenance costs? Okay, again here we want to have a solution, right? So there are two scenarios here, and then X represents the number of apartments, right? So we want to know that what is the maximum number of apartments and what is the small number of apartments. So if Mr. Nxana and his company, they build these properties, they cannot build more than 500, because at most means less than or equal to. At most, that's what you need to know. So they cannot build more than that, so X will always be less than or equal to 500. And then of course Mr. Nxana have a choice of building the properties or not building anything. If he is not building anything, he will have 0 apartments. If he is building, once he start building, he will start to have either 1 apartment, 2 apartments, 3 apartments, and so forth. He cannot say I have negative apartments. So he can either have 0 or any value less than or equal to 500. So what we are having here, we are just having X is an element from 0 to 500. So X can take any value in between here. Of course, when we are actually having there are different interpretations. When someone is saying I have X is equal to 10,5 apartments, they are different. We are not there yet. what we want to find out, what is the max, what is the, here we're looking for how many we want to minimize the maintenance costs. We want to minimize. So the first thing that you need to find out, we did, which is the endpoints, this endpoint and that endpoint. And then the second thing you wanted to do here, you wanted to check endpoints or the output, check outputs for the endpoints. So that's what we wanted to do. And then when we are doing that, all you need to do here, you wanted to find, if let's say x is equal to 0, what is the output? So you go to the equation there and then you say I have 0 400 plus 14, where there is x, I plug in a 0, minus 0.04 x squared, but in the value of x I'm gonna plug in a 0 and then I'm gonna square it. Anything multiplied by 0 is gonna be 0, anything multiplied by 0 is going to be a 0. So this one is going to be r 4,000 or 4,000 rands. And then the second thing that you wanted to do, you want to check this one have been checked. I want to check this one, and then we're looking now for C 500, and then of course here you will end up having 4,000 plus 14 times 500, and then minus 0.04, and then you place a 500 inside and then you square it up, just to make sure that we did that. Okay, so we will have 4,000 here, 4,000, and then plus we have 14 times, and then here you end up having the 500 inside, and then you have minus 0, 0.04, and then inside I will have a 500, and then of course I am going to square it up. So the answer that I'm getting here is going to be 1,000. So here I will end up having 1,000 rands. So I will have 1,000 rands. Hopefully I did what needs to be done. I have 14 times 500, and then of course here I have 0.04, and then I have 500 squared. So I think that is nice. And then the second thing I want you to notice here, you can see that producing 500 properties is actually creating costs that are less than the cost of producing nothing. So that is what is important here. You can see that producing is actually helping us here. I know that most people are usually thinking that buying the property, and if I haven't produced any property, you find out that I'm not having any costs. That is not always the case. Sometimes you are actually having costs, and by producing you actually have minimized the costs. And then now we wanted to check the turning points, so we need to first find the turning points. So you just say turning points, right? A turning point is always going to have an x and y, and to get this one, you set the first derivative equal to 0. Set there the first derivative to 0, and then to get this one is just going to be you plug x in the original given equation. So that is what you actually do here. So the function that we had here was very nice. It was c of x, it was equal to 4,000, and then plus 14x, and then minus 0.04 x squared. Just to double check that we're still on the same point, 4,000, 14x minus 0.04 x squared. And then the first derivative of this particular function here is going to be the derivative with respect to this variable here. So it's going to be x, and then I'm going to have 4,000 here plus 14x minus 0.04x squared. And then of course here the derivative of a constant is always going to be 0, and then plus the derivative of 14x is going to be just a 14, because this one here is the same as just y is equal to 14x, and of course this is the gradient. That is why the derivative is going to be a 14. Or if you wanted to use the power rule, you pull out the 14 and then you take the derivative with respect to x of x, and then of course there is a 1 there, so this is going to be 14, and then you bring the 1 down and then you multiply by x raised to 1, and then you subtract a 1 there. Of course this is going to be 14 times 1 is just 14, and then I have x, 1 minus 1 is 0, x to the power 0 is 1, so you have a 14. Whichever way you want to look into it is fine. And then here of course I'm gonna pull out 0.04 out, and then I take the derivative of this, and the derivative of that is just going to be 2 times x, and then 2, I raise a 1, so we are left with a 1 there. And then of course 0 plus 14 is just a 14, and then I will end up having a minus 0.04 times 2. Of course that's simply a 0.08 x, so 0.04, and then you multiply it by 2, that's supposed to be 0.08, and then we have that. So that is the first derivative. The second thing, you wanted to set this equal to 0, so you'll have a 14 minus 0.08x, you set it equal to 0, and then I take this 14 to the other side, so I will have minus 0.08x must be equal to, this was positive, that side is going to be a 14, and then of course I then divide by minus 0.08 on both sides, minus 0.08, and then I will end up being left with x is equal to, because this one and that one will cancel out and I will be left with that, so I will have 14, and then I divide this by 0.08, so I have that nice thing here, which is 175. So I have 175 what? Apartments. So if I have 175 apartments, what will be the cost for that? So this one here is the output, or these are the costs. So I'm going to plug in here 175 in the original function. So this one is going to be 4,000, and then plus 14, and then instead of here I will plug in 175, and then after that I will have minus 0.04, and then I have 175, and then I have to square it. And then after that, what will that be? I will have an R there. I will have a 4,000, and then plus I have a 14, and then after that I have 175, and then after that I will have minus 0.04, and then inside here I will have 175, and then after that I will square it up, and then I will get something nicer, which is actually a 5,225 rands. So these are the costs if I produce this much. Can you see something here that if I'm producing nothing, I will end up having a cost of 4,000. But if I'm producing 500, I will have a cost of 1,000. But once I am in between, I produce 175. The cost that I will be having here will be more, which is 5,000. Of course, this one cannot be the mean at all, because this one is already bigger than the endpoints, so we cannot take that. And then now the last one will be I have this one, this is the only value, so this one cannot be one of them, so the minimum can only be attained if I am actually selling 500. If I were to place in 500 here, just to double check if I'm getting the same thing here, if I'm placing a 500, so it's 1000. So I'm actually having this one is max. So building X is equal to 500 apartments. Will minimize the costs. So that is what is important here. What is the value of X that is actually making this function have the lowest output? That was the meaning of this particular question. So you can see that producing nothing is not the right way, but producing up to the maximum value we can is actually going to actually minimize our costs. So that is what we are looking for, because 170, where's this function here? Yeah, 175 is actually not helping anyone here, because what is basically happening here, this is 175, and then when you're plugging here 0.04, and then here we are also having 175. So in that particular case, you find out that this number is way more than, it's more than 4000, and it's also more than 1000. So this is much, we cannot use that. We want to minimize the cost, so just produce or build as many apartments as possible so that you can minimize the costs. Another example will be, suppose we have Miss Nala, and Miss Nala has 2,400 meters of fencing. In other words, if you are using wire, you have a wire of about 2,400 meters, and she wants to fence off a rectangular field that borders a river with a straight bank. She needs no fence along the river. What are the dimensions of the field that has largest area? Let's start by talking about this 4,000 meters fencing. So Miss Nala is either having a wire of this long. So this is how long the wire is. So you find out that from this point here to that point, the length of this wire is actually 2,400 meters. That's how long this wire is. She has that, and she wants to fence. So what she wants to do, we are actually having a river here. This is a river this side, so we are having a river there, and then she wants to create a rectangular shape. So she wants to create a rectangular shape. So a rectangular shape is going to be something like this. This is not good looking at all. Let me use a ruler here. I grab my nice ruler and then I place it there, and then I grab it and then I deal with that, and then I also deal with this one here. So this is the river. So this side, she is not actually going to fence this side. So she wants to create a rectangle, have 4 sides, but this side here will be using a river, because cows cannot jump the river and be here or whatever. Maybe this river is one of the biggest rivers whereby nothing can jump from this river and go there. So she is safe to actually create this side. Maybe she's creating a farming business or whatever, but she's using a river there. And then what this question is saying, what are the dimensions of the field that has the largest area? So this question is saying, what is supposed to be the length of this side? What is the length of this side? What is the length of that side? And what is the length of that side? What is important here is that we don't know this length. I'm gonna call this length x, And of course, because this one is supposed to be a rectangle, in a rectangle, this side and that side needs to be the same. So this side is also going to be an x. But that side is not really equal to this side and that side. So I am going to call this side y, because we don't know that side, but all we know is that this side and that side is supposed to actually be the same, or they're supposed to be equal. So this now is the area. This is the area. So we want to maximize this area. But what is important here more than anything is that this side, we are going to use this wire to fence this side. So we want to fence this side. So this side here is going to take some time, or some length of this wire. So we are going to cut a wire somewhere here so that we can fence this side. So this side from the wire, so the length of this, we need a wire of length x, or a fence of length x, so that we can place it here. And then we also need some wire here that is going to fence this side. So this wire here is going to be somewhere there, and then it's going to end there. So we need a y there, and also we're gonna need this side here, which is going to be x. So we have this x there. What is the meaning of this whole thing? Is saying that if I were to take x and I plus a y, and then I plus this x here, so x plus this plus that, it should give us the length of this wire, which is 2,400 meters. Or you can say that x plus x, there are two like terms, so you can add them. I have one x here, I have another x there. So how many x's do I have? I have 2x plus a y is going to be equal to 2,400. Or I can clearly say that I want to make y the subject of the formula. So y is going to be 2,400 minus 2x. So as long as I can find my x, I know what y is, because I'm just going to plug in x and then subtract that in 2,400. And then the next thing that I want you to know here, we want to maximize the area. So what is the area of a rectangle? So the area of a rectangle, we know that the area of a rectangle is given by, you just take one length and then you multiply by breadth on this side and that side. So if you look into this one here, you will find out that the area of a rectangle, I'm going to just place an x there, you will see why. The area of this rectangle with respect to x is going to be, what is the length? The length, I'm going to say it is going to be x, and then what is there? So you take one side and then you multiply by that side. So it's going to be x times a y. And then of course I know x is going to be x, because I want this area to be a function of x or a function of y. So in the value of y, I am going to plug in 2,400 minus 2x, or 2,400. And of course, if you look into this, you'll find out that it is 2,400 times x minus 2x squared. So I have a of x is equal to this. So this is the area function, or this function is the area with respect to x. Now, how do we maximize the area of a function? So to find the maximum area here, what we need to do here is this. I want you to take note of this whole thing here. So if, let's say, I were to just increase this y here, I increase this y. So by increasing this y here, what I would end up having here, I would end up having no height here, or no let's say x will be 0. So if I'm increasing this y to be so large, in other words, I'm just gonna place my wire to be just flat like this, so I don't have this side and that side there. So what will actually be happening here? So what would happen here, I would end up having a straight line. So I would end up creating a straight line here, which is actually not a rectangle. So in order for me to actually end up having a rectangle, I need this side here to be bigger than 0 and this side to be bigger than 0, even if it's 0.01, but I want it to be there so that I can create a rectangle. A rectangle is a shape of this kind here. So if this side is 0, I will end up just having a straight line, which is clearly not a rectangle. So if you look into this particular equation here, my x need to be bigger than 0. That's what is important in here. And also, if you look carefully into this, right, if my x is actually 0, my y is actually going to be, if x is equal to 0, so this is going to be 0. So our y, x is equal to 0, this is going to be 0, our y is going to be 2,500. 2,400. And then another thing that I want us to look at here is this. If let's say, because this is also very much important, if let's say I am actually creating, deciding that my y, I want my y to be actually a 0. So if my y is actually a 0, what is going to happen here is going to be, I will end up having a straight line of fencing that is like this. So if let's say I'm just let's say this one was a river. So this one was a river, and then I create a straight line here. So the length of this y will actually go all the way up, and then the value of x, this is actually much more important. If let's say I am going all the way and then I go there, and then after reaching that point I go back again, in other words, I flipped my wire to go all the way and then started to come back, then my x here will end up becoming half of this wire. So we'll end up actually becoming half of this wire. So what will actually happen here, we'll end up having 2,400 divided by a 2. What we did actually here, we just made this equal to 0, and then we took this to the other side, and then we solved for x by dividing this by this 2. That's what we ended up having here. And of course, if we have 2,400 and then you're dividing by 2, you will end up having 1.2. So our x actually is going to be somewhere 1,200. So it cannot really reach this, because if I am actually doing this and it's going all this way, and then it comes if I'm going all this way and then I'm coming back, I am not having a rectangle here. I just have a straight line, so it is not a rectangle. That is why we don't have equal here. That is why we don't have equal here. If it happens that you place an equal there, you will end up losing 0.5 of a mark out of all the marks, because it's not that deep. And also, even if you just decided that when y is equal to 0, instead of going up and then you go down, and then you end up not instead of going up and then coming back with your fencing, you just go all the way up, and you say that our x is less than x is bigger than 0, and it is actually less than 2,400. You're supposed to actually lose also 0.5 of a mark. It's not that deep. But what is important here, you must know that we are actually having this one here. We're actually having this and that, but there is no equality. So there is a mark for knowing the interval. There is a mark for knowing the interval. The mark is for actually knowing this whole thing, drawing the picture that you know what you are doing, and also finding this equation here of course you have some nice equations, and then you also have this here. Usually this question can be about 7 marks depending on the available marks, but I'm just trying to show you that there is a mark for knowing this, there is a mark for knowing that, there is a mark for knowing that, there is a mark for knowing that. But if the marks are minimal, you find out that you'll be given a mark for 1 here, and also 1 here and 1 here, and the other remaining marks are distributed in what we are about to see here. Now the first thing that you need to do here, remember that we have x, our x is between, now we're not using square brackets because 0 is not included, so we're using open brackets, and then we have 1200, and then we're using that also. So the first thing we need to find, what is the area if x is equal to 0. So if x is equal to 0 and want to find the area, we'll end up getting 2400 times 0, and then minus 2, and then we have a 0 squared. Of course this is going to be 0 meter squared because we're multiplying meters by meter, so it's going to be meter squared. So this one here, by just looking into it, this cannot be the maximum area. So let's look now at A of 1200. What will that be? Of course it's going to be 2400, and then we're gonna end up 1200, and then minus 2, and then I have 1200, and then I square it up. What is this gonna be? So we'll end up having 2400, and then I multiply by 1200, and then that one here, and then I'm subtracting 2, and then inside I will have 1200, and then after that I'm going to square this thing up, and then I end up actually getting an area that is 0 meter squared. So of course 0 is not a maximum here, it cannot happen. So now we want to check the turning points, so we check the turning points. So here I wanted to find the first derivative of the area. Remember that the area was saying I have 2400x minus 2x squared. Let me check it up. Yeah, 2x squared. And then the first derivative, of course, what is the derivative of this? Is just going to be 2400, and then minus, what is the derivative of this? I'm going to bring this down. I will end up having 4x. So we'll end up having a 4x, and then now I set this equal to 0 so that I get 2400 minus 4x is equal to 0, and then I take this to the other side. I have minus 4x is equal to 2400. Because it was positive, it's going to be negative that side. I divide by minus 4 this side, I divide by minus 4 that side. I end up having x is equal to, because this and that will cancel out, and then I will end up having, I have minus 2400, and then I'm dividing this by a minus 4. So what is the answer? X is equal to 600, and then once I get x is equal to 600, I just check what is the area when x is equal to 600, and then you find out that I will get 2400, and then I will have 600, and then minus 2, and then I have 600 here, and then I square it up, and then of course here you will end up having, I have 2400, and then I multiply this by 600, and then after that I subtract 2 times, I have 600, and then I square it up. So the answer that I'm getting is going to be 720,000. That is what we are getting here, meter squared. What does that mean? This actually means that, because if you look at 720,000, so let me write this here. Since A of 600 is bigger than A of 0, and A of 600 is bigger than A of 1200, what is actually this saying? It says that then the area will be minimum if x is equal to 600 and y is equal to, because if you are looking for the dimensions here, you need to have your x and also have your y, because x represents this side and that side, and then we need the y. What is our y? Our y is 2400 minus 2x. So our y, we know that is going to be 2400 minus 2 times x, which is 600, which means our y is, I have 2400 minus 2600. So this is actually this is just 1200. So this needs to be 600 meters. This one also need to be 1200 meters. So that is what is important here. You can see that if you add this one, you say to plus 2 times 600, you're supposed to get minus 2 600. Let me see, I wanted to, what am I doing here? If you are taking 600 and then you multiply by 2 and then you add 1200, you're supposed to get 2400, or 2400. So this is actually what is happening with this example. That's what they were looking for. So by knowing this, there is a mark. By knowing that, there is a mark. Sometimes this is 0.5 and this one is also 0.5, and the reasoning here, you usually get something also. And then secondly, by knowing the turning points that you deal with, the turning point, you find the derivative, there's usually some marks there. And this one usually depends now on how the examiner usually look into this, but it is important to know this. It is important to know that. It is important to find the area, and it is also important to actually check these points out, and it is also important to know the turning point, and it is important to compare and then have this. In other words, try and write everything you can write out of this, so that you can get your final answer. So that if it happens that your answer is wrong, it is wrong, but at the same time you get some marks on what you wrote above. That's what is important. But if you are not writing everything and your answer is wrong there, you actually get 0 marks. So it is important when you're dealing with these problems to write everything. Now I want us to write this example here. I want us to actually do this example, but I want you to take 2 minutes and copy this thing up, and then I will try and explain what is the meaning of each of these things, and actually how can we actually solve this question, and then we'll call it a day. This example is saying given the pressure P is equal to 4000 dynes per centimeter squared, and the viscosity eta of 0.027 of blood through an artery of diameter D, which is equal to 0.016 centimeters, and the length is given as L equal to 2 centimeters. Find the velocity of blood at distance R is equal to 0.02 centimeters away from the center of the artery. The second question is saying find the velocity gradient at distance R is equal to 0.02 centimeter away from the center of the artery. Okay, what is happening here is saying, okay, let me reread this again. Given the pressure P is equal to 4000 dynes per centimeter squared, and the viscosity eta are equal to 0.028 of blood through an artery of diameter D is equal to 0.016 centimeters, and length L is equal to 2 centimeters. Find this velocity of blood at a distance. So basically here, this is the only information that is given, and now we want to find out how can we actually solve this. Let me first explain some few terms here. So what do we mean by dyne? What do we mean by viscosity? Of course, we know that the diameter, if let's say you have a circle, the diameter is the length from this position to that position, or it is 2 times the radius of that circle. So we know that. So what is the pressure? We know that the pressure is the force applied divided by the area whereby the quantity of interest is passing through that area. So for instance, if let's say we had a cylinder here, and now we have water going through, or we have or we have blood that is going through this cylinder or through this pipe, or we have blood going through, or water that is passing through, you will find out something like this. Let's say you had a syringe, for instance. Suppose this is your syringe, and a syringe usually looks something like this. So it usually looks something like this. And you have a pistol here, and of course here you have something of this kind, and here you end up having this place here. So if let's say you push here, so you are pushing here, right? So if you are pushing in this pistol, and then this one is pushing the water that is here. If let's say this one is water, is pushing this water here, you will find out at this point here, there is this area that is inside here, or this circle that is inside. So this pistol is pushing through this particular area. So the pressure is going to be the amount of force that is pushing this pistol down there. So we will end up having force per unit area. So the force per unit area is what we usually call the pressure, or force applied per unit area. So that is actually the pressure. That is the meaning of a pressure. And also at the same time, which means the units of a pressure is supposed to be newtons. Newtons it's supposed to be newtons. Newtons is n, so it's supposed to be newtons, and then here is supposed to be some meter squared or centimeter squared, or it is millimeter squared. But these units should be for area, and this one should be for the force. So those are the units for the pressure, so it's supposed to be meter squared here. But if what we are dealing with have smaller units, we usually end up using centimeters or millimeters here in the denominator. And then now that's where now dynes comes into place, because one dyne, we know that one dyne is equivalent to 10 raised to minus 5 newtons. So one dyne is equivalent to 10 raised to minus 5 newtons. That is the meaning of a dyne. I don't want you to get too surprised that, hey, what is a dyne? A dyne is just 10 raised to minus 5 of a newton. So that is actually happening. And then, what is viscosity? Viscosity is the resistance of fluid. It's just the resistance of the movement of fluid. So if let's say you have maybe some pipe, and you want to water pass through, what is the resistance of this particular fluid to move forward But in simple terms, you can just think of this is this. Viscosity, think of it as how thick the fluid is. If the fluid is too thick, you know that if the fluid is too thick, it cannot move easily. But if it is less thick, you will find out actually that water can just flow very easily. So the viscosity of water, we find out that it is so small. And then when you're looking at blood, if you're not drinking enough water, you will find out your blood is actually getting thicker and thicker. Now is struggling to move through your arteries, and now you end up starting to have issues in your system, and then now you end up needing a doctor and all those things. But what is important is that how thick the blood is actually characterized by viscosity. That is what I want you to actually remember, and you know now the diameter, you know, and also you know the length of this the length is given for a certain artery. I've just talked about pressure, and I think maybe you get some understanding, and viscosity, you understand that it is just how much this fluid is resisting to move forward, or it is just how thick the fluid is. And then we talked about, you know, what is the diameter. I want us to analyze this problem little. Suppose that you are cutting an artery. So you had an artery. So this, I'm going to say that this is your artery or your vein. It is your artery or your vein. So the reason we're actually having this pressure here, most people are asking, but say, who is applying the force if I have blood in my system and then it's moving in my arteries? What is important is that the heart is the one that is actually pumping that blood. It is the one that is applying some force to make sure that the blood is actually moving in your system. So suppose you had an artery maybe somewhere in your system. This was your artery somewhere, maybe in your hand, or somewhere in your leg, or somewhere in your brain, or somewhere in your internal intestines, or in some internal organs. And then I'm cutting that artery, and then I'm zooming it in. This is saying that once I zoom it in, you will find out that an artery will actually have an opening like this. So we'll end up having an opening in that artery, and then this side also will end up having another opening this side. And then if you look carefully according to this problem, they are saying that if I were to cut this artery, I want this artery of mine to cut it to be equal to 2 centimeters. So moving from this position here and this position there, this I want it to be 2 centimeters. And then secondly, what is this problem is saying is that there is some center there. Suppose that this is my center, so I'm gonna say this is my center. And then once you have this, we know this was given, and now want to talk in terms of diameter. So if I want to find out the length that moves from this position to that position, we know that the length from here to there is going to actually gonna be this length from here to here is going to be d, which is equal to 0.016 centimeters. And then of course, when that is actually given this diameter, which means the radius is actually given to move from this position to that position. So this radius here, I'm going to call it r, which is just a half of the diameter, which is that. So it's going to be 0.08 centimeters. So the half of this is supposed to be that. So this is going to be r. So what is this question saying? Is saying that they want you to find the velocity at the distance r is equal to 0.02 away from the center. So we have this center here. So to move, let's say, from the artery, from the center of this artery up to here, we're gonna call it r. So this one is actually given, but it is what is actually changing. This one is actually fixed. Now, here comes what is important. I want you to know is this: if you were to have, you were to open water in a tap. If let's say you were to open your tap, you have a nice tap. Maybe this is your tap. You have a nice tap, something of this kind, and here it is something like this, and then it has some water there. So if you have this tap here, you will notice something here that here, if this water is coming out, that the water that is actually if let me try and make this a little bit clear. I have this pipe here. You will find out that towards the center, water is actually running too fast, and also as you are moving away from the center, the water is not running too fast there, and also it is not running too fast as you are going, and it's actually the speed here is smaller than the speed at the center, but the speed here is also smaller than at the speed of this one, and also the speed of this one is less than the speed of the water molecule that is moving here. And also another thing that I want you to notice, that when the water is actually hitting the edges here, you will find out that once water hit the edges at this position here, if this is this, if water is hitting this, you will find out here that the velocity is actually 0, because once the water is hitting here, it's actually end up hitting here and coming this direction, and it's affecting the water that is towards the edges here. Hence this water here is actually moving slower. The same thing here happens if you are actually looking at the model of blood, that at the center, blood is moving too fast, and then as you are going here, it's not moving that much, because the water that is towards is at the end or at the edges of the artery is actually not moving at all. It has a velocity of 0, and also at the same time, once water hits here, it actually starts to disturb the water that is here closer, and when this molecule is affected, it also affects somewhere here. Even with blood, that's the same case. Now, and in order for you to see properly if this friction is actually happening, you end up seeing that if you have a tap here, some water is trying to move this way and some water is trying to move this way, because they are actually feeling the pressure of this water that is coming out, but this one is actually moving very faster and is actually straight. So that is what is happening in an artery. Now, how do we end up finding this velocity here and also the velocity gradient? The velocity gradient is simply the derivative of this function if we can find it. The good news here is that there is nice French. Why am I saying nice? It's actually good. It's actually one of the well-known French physicians, which goes by the name we usually call this physician Jean Louis Mary Zenil. And Jean actually in 1840 he actually discovered what we call the law of this is a bad writing here. The law of laminar flow of fluids. In fluid, this is not fluid. Why am I writing wrong things on my birthday? I don't understand. This one here, we're actually having fluids. So it is a laminar law of fluids, and he discovered that the velocity. So what is this velocity? If we were to look moving from the center, either we're moving that side or we're moving to that side, he found out that the speed the speed or the velocity of this fluid. R is actually the distance from the center, and then this is supposed to be the same as the pressure divided by 4, and then you have eta, and then you have L, and then inside here you have R squared minus small letter r. So this one is the radius of the artery, and then this one here is actually the distance from this center here. So Jean actually found this out, whereby this one is actually the pressure or the force per unit area, and then this one is viscosity or how thick the fluid is, and then this one is the length of the artery, like this here if you are looking into this diagram here. And if you look carefully into this here and looking into what is actually given, you will actually find out that we have all these things here. So to actually answer the question in A here, you will find out that A was actually saying find the velocity of blood at a distance 0,02. So R is given as 0,02. The capital letter R is just the half of this. L is given, and then eta is given, and the pressure is given. So what you actually do here, you want to find V of 0.02, which was given. So the pressure was 4,000, and then you divide this by 4, and then you have eta, which was 0.027, and then L here is supposed to be 2 centimeters, and then inside here, what was R? R was 0.016 divided by 2, and then you have to square the answer, or you can just simply say that it is 0.08 squared minus R, which is 0.002 0.002 squared, and then you can find out the final answer here. One thing that I want you to notice here is this. I want you to notice that 4,000 was given in dynes per centimeter squared, and we know that dynes is still fine if we are using centimeters, but if we want to use newtons here, we wanted to use meters down there. And also another thing, because this one is actually in centimeters, and also another thing here, viscosity is given, and then this one is in centimeters and this one is in centimeters. Because I have centimeter in centimeter, I don't have to convert anything, I just have to plug in everything there. But if one of these things, let's say maybe the length was in meters, then I would have to convert those meters to centimeters. But in this example, it is a very nice example. So here we end up having something that is, you have your 4,000, and then you divide that by 4, and then you multiply by 0.027, and then you multiply by 2, and then of course at the end here you have 0.08, and you square it up, and then you subtract 0.002, and then you square it up, and then you have your final answer. Your final answer is going to be, I think it's supposed to be 118.4. When you are having a bar, there is saying that you have 4 dots, so we'll keep continuing with 4, or you can just say it is 118 point, and then because we are going to round off what is happening after this whole thing, so we're just gonna place a 4. And I want you to notice something here, that we have this nice approximation here. So we have this nice approximation that is actually happening in there. So that is what is nice about this whole thing. And also another thing that I want us to do here is let me see here. I'm just trying to see if I wrote everything the correct way here. 0.08, and then we have 4000, you have that. So we're actually having something of 1.18, and then of course I think that's it. What is important here is that you know how to plug in. And then when it comes now to B, we wanted to find the velocity gradient. So most people will think that because this one is velocity, when you're taking the derivative, we're supposed to get acceleration. That is not the case here, because we are taking the derivative of this with respect to r, not t. So if this was time, then it was going to be acceleration, but now this is just r. So to get the velocity gradient, so what we are actually looking for here, we are looking for v prime of 0.02. So to get this, first we need to find v prime of r, and you know that v prime of r is just gonna be the same as the change in v of r, and then with respect to the change in r. But now we want it at the exact time, so this is an average rate of change, but now we want it at r. In other words, we were looking for the instantaneous rate of change. In other words, we'll end up having the limit as delta r tends to 0. Or you can say that, because some people say this is actually the derivative, or you can just say I'm looking for dr of v of r, or simply I am actually looking for, because the function was given there, so we are actually looking for the derivative with respect to r, and then inside we are having 4, and then inside we are having a p divided by 4 eta, this is eta, times L, and then as you are going there, you will find out that inside I ended up having a capital letter R minus small letter r squared. And if you look carefully into this, you will find out that this is a constant because it's given. This one is a constant, this one is a constant, and this one is a constant. So whenever I want to take a derivative, I always take the constant out of the derivative with respect to r, and then we take the derivative with respect to r of r squared minus r. And of course, you know that the diameter, the radius of the artery is just this much. It has this radius, so it's not going to change, but the position in the artery are away from the center of that artery. You'll find out that it keeps changing. So if that is the case, because this one is always gonna be constant, it's not going to change, so we're still gonna end up having p divided by 4 eta L, and then inside here the derivative of this is going to be 0 because this is not changing, it's a constant, but this one is the one that is changing, so you end up having minus, and then you bring the 2 down, you have your r, and then you subtract a 1, and then you're left with a 1. Or simply put, you are actually having p divided by 4 eta L times minus 2r. And if you look into this this 2 and this 4, there's something that can be done to say now v prime of r is just the same as this 2. I'm going to cancel this 2 and this 4, and I'll be left with a 2. So I'll end up having a p divided by 2 eta L, and then I have a minus 1 here, so I'm just going to place a minus there. And if you are looking now for v prime of r, you will actually find out that now we're actually having minus, instead of p, you have your 4,000, not 400. You have a 4,000. We also have this r here, I forgot it. You have an r there, and then here you will end up having an r which was 0.002, and then you divide this whole thing, and when you're dividing it, you have a 2. Eta was 0.027, and then here we ended up having another 2 for the the length here. So this whole thing will end up becoming, let me plug some values here. So we're actually having here minus 4000, and then I multiply by 0,002, and then I divide this whole thing by 2, and then I divide by 0.027, and then I am multiplying that by 2, and then we get something there which is this is actually negative 74.074074, and then it continues, or simply I'm going to just take the approximation of this. Is going to minus 74. I can just say minus it because this is going to be, or 0.1. Yeah, I think this is actually going to be what we're looking for, but here, because we are evaluating supposed to be 0,002, of course here we have a prime 0.002. That's what we are actually looking for. And of course, if you wanted to look into this here, this one here was the speed. So the speed is always going to be, because the units we're using here were centimeters, so we ended up having centimeters per second. So that is actually the speed. And if you look for this one is supposed to be, remember that this is actually the average. That is why I wanted to write this first, so that you can see units wise that we have units of the speed, and then we are dividing by the units of the distance away from the radius. So here we'll end up having centimeters per second, and you can even say that per centimeters again, so that you can see that those units where the units are coming from the denominator, because we're having delta VR of VR with respect to delta R. So this centimeter is coming from that, and we know that the velocity have these units. That is why I'm writing it like this. I'm not simplifying it, because I want you to get that these are the units that we are actually using, and I don't want you to actually make any mistake there. So that is actually what is important here. I am going to end here for this particular lesson here, and then what I also wanted to realize here is this. You know that we are close towards the date for our second test. Our second test is supposed to be on the 12th. I think, yeah, it's supposed to be on the 12th. So I've tried to sacrifice some hours on my birthday to make sure that I have this lesson. So try and make sure that you learn as much as possible, because you still have some days. I think it's more than 12 days. So try and learn as much from this from these lessons that I've uploaded, and also make sure that you practice, so that when that date comes you are already fit, because there is a lot that is covered in test 2, and most cases you find out that it is starting to be way different from what you were doing in high school. That is why it becomes a lot. So practice as much and see if you are actually in the right direction. Thank you. I think I will stop there, and then the next lesson will be on L'Hopital's rule, which is one of the most important rules in mathematics, and also in solving limits. So basically what happened is that L'Hopital's is one of the mathematicians that actually acquired some of the rights from the Swiss mathematician John Johann Bernoulli. So I think they ended up they have a very intriguing business arrangement, those two. Somewhere around around the beginning of understanding this L'Hopital's principle. I think actually I'm not only thinking, there is some information on this that L'Hopital's acquired some of the rights of the mathematics that was actually discovered by Bernoulli. But we'll look into that in our next lesson. For now, just make sure that you understand these nice things here. And also, if you are dealing with a minimization problem, what is important, make sure that you know the endpoints, and then after knowing the endpoints, you also know the turning points and their outputs, and then you compare the outputs. Once you compare the output, if you're looking for the maximum, and then you look at the x value that is producing that, and that we're looking for. If you're looking for the minimization problem, you can see that we tried to do some nice examples here with money, with the profit. Yeah, we looked at profit, we looked at costs, we looked at area, and then we started to look at what is actually affecting you now, the blood flow, and we also looked into the position, velocity, and acceleration, because I know that you're gonna buy a car once you get employed, so you need to get some understanding there. And also, of course, you don't just want to waste your money, you also need to invest and see that you are making a profit or a loss. And also, you need to manage your costs very well so that your money is not just going anyhow. And of course, this is also affecting those who are doing pharmacy. If you look into this problem here, that you cut an artery, and then once you cut an artery, it's going to actually have this, and also it has a sender. I'm making this so big because if you are cutting your artery, you're not gonna even see this. I was trying to make it so big so that you can actually see what is actually going on and how you can actually apply this law of laminar flow, which is characterizing how the fluids are actually flowing through a pipe or a cylinder, or how is your blood actually flowing through your artery. This is the law that we are using, which was discovered in 1840 by Jean-Louis Marie Boissonnaire, and I think we end it there. Thank you.